So now let's look back at our example from earlier when we were thinking about our curve as a piecewise smooth curve. So let's let C be a path composed of smooth curves C1, C2, up through Cn if f is continuous on C, then when I compute this line integral over C, I can break it up into the separate components of C, the separate parts, so I can compute it as, sorry, that should be x comma y. F of x comma y ds plus the line integral over C2 plus all the way up to the last part of your curve C in so you can split your line integral up over the separate parts of your line integral. So let's look at an example. Let's evaluate the line integral C of x ds, where C is the piecewise smooth curve shown. So this piecewise smooth curve, it's going to start off at the origin. It's going to go up to the point 1, 1 along the part C1, which is given by y equals x. And then it's going to go back to the origin along C2, which is given by y equals x squared. So if I want to compute this line integral over C, I need to break it up into the line integral over C1 and the line integral over C2. So let's start with C1. So how can I describe C1? Well, you need to use parametric equations to describe that. So if I use x equals t, well, I know t goes from 0 to 1. And the equation is y equals x, so y would also be equal to t here. So now let's compute x prime is 1, y prime is also 1. So now we can compute our line integral over C1. Well, x gets replaced by t, so this becomes t. And then we're going to look at the square root of x prime squared, so 1 squared, plus y prime squared, 1 squared. And t goes from 0 to 1. So I'm looking at the square root of 2, 0 to 1 to t. So I'm getting the square root of 2 times t, t squared over 2. So I'm getting square root of 2 over 2. So now we found the line integral over C1. We now need to find the line integral over C2. So C2 This is the parabola. So x, so I'm going to also use 0 to 1 for t here. X starts off at 1 and it decreases down to 0, so it's going to be 1 minus t. And because you're using the parabola equation, y is x squared, so y will be 1 minus t squared. Now we are going to need the derivatives of these, so let's go ahead and compute those. We get -1 for x prime, y prime. You got to use the chain rule. -2, 1 minus t. And so now let's compute our line integral over C2. So x gets replaced by 1 minus t. And then the square root of -1 squared, which is 1. And then you're going to square this as well, so you're going to get 4, 1 minus t squared. And here we can do a substitution. First on, let's substitute u equals 1 minus t. So I'm going to get a negative, oh, I forgot to put in my bounds. T goes from 0 to 1. Negative u, the square root, 1 plus 4u squared du, and I have a -1 out in front. Now you do need to change your numbers. Plug these in place of t here. So if I plug in 0, I get 1. If I plug in 1, I get 0. So now, if you look, you simplified it a whole lot. I'll maybe go ahead and if I flip these bounds, it's going to get rid of that minus for me. So let's go ahead and do that. I can do another use substitution here. So let's say v is going to be 1 plus 4u squared. dv is 8u du. So you're going to get a 1/8 out in front. 1/8, the integral of v to the 1/2 dv. Now change your bounds again. If you plug in 0 into here, you'll get v is 1. If you plug in 1 into here, you'll get v is 5. And now you just need to compute this integral using the reverse power rule. This would be, let's see, v to the 3/2 over 3/2 from 1 to 5. If you simplify your fractions here, you'll get a 1 over 12. V to the 3/2. So 1 over 12. 5 to the 3/2 minus 1. So now you found the line integral over C1, you found the line integral over C2, so the line integral over C is just going to be the sum of those two. So plug in what we got for the first one, it was square root of 2 over 2. What we just got for the second one, 1 over 12. 5 to the 3/2 minus 1. And there's my answer.